Okay, and so we can see here that they're labeled. And so if we look here, these right here, A and B here, would end up being coupled. 2, this has to be ruled out because we have C and D that would be coupled. And we look over here, again, these would be 3, these would be 2 right here, right? This would be 2 hydrogens here, okay? And so we look over here, and we get E, F, and another set of E, because remember, these are the same, right? Everybody see that symmetry there? And so we notice that these are actually not coupled right there because they're quite far away. And then we look over here, and these is only one set, right? So we don't have any other peak. We just have one peak, okay? And so they're singlets, so they have to be not coupled, right? If they were coupled, we wouldn't have singlets. We'd have a doublet, triplet, depends on how many chemically distinct protons were next to it, right? So these right here would not generate singlets. This one generates singlets, but it would only give us one peak, right? And so the only valid option is this one right here, of course. Okay. Did everybody understand that? Did I lose anybody? Fantastic. Anybody have any questions? All right. Let's go ahead and start covering material. Okay, so let's talk about the origin of this rule, the n+1, the doublets. So the origin of that n+1 rule, this can actually be fairly easily understood if we consider the various magnetic fields, or B local, that are generated by our sets of protons that are responsible for splitting a particular signal. So if we think about it this way, there are two possibilities for this hydrogen to exist in, right? We could have the upspin, we could have the downspin. Okay, or another way of saying it, it could spin this way, it could spin this way, right? And so there's two states that can be in. And so this right here, there's no difference between these spins if there's nothing to interfere with it, right? But if there's something to interfere with it, do these hydrogens necessarily have to have the same spin? No. And so if we have different spins, they're going to be interfering with each other, aren't they? Or another way of saying that is we have two possible states. They match, they don't match, right? Okay. And so n+1 gives us two possible states, doesn't it? Yeah. And so that's all that is it's the number of possible matchings that can occur in these. Okay? So they either both match, or they don't match, right? And that's actually why we see these probability distributions. Did you guys just finish a probability exam?
No, simple means.
Oh yeah, so you guys just finished some probability, didn't you? Yeah, I mean technically, yeah. So you guys should know probability pretty reasonably well. So if you look here, if they both match, they both match down. That's going to give you this state right here. Okay. So that would give you these states right here, and those only have one possible outcome there, right? Can everybody see that? And so this one that's about double the population, what do you notice about the possible outcomes that would be the same? It has degeneracy, doesn't it? See that? So when they don't match and don't match, that actually gives you two degenerate states, doesn't it? And so that gives you the highest amplitude, the highest intensity. Okay? Mm-hmm. I'm sorry? So the integral would increase by double. Yeah. Which is why the height isn't quite double. Is because remember, it's always the area, the integral. So the integral increases by double. It wouldn't be a square function, but yeah, it's an integral function. Depends on the width. So if you managed to get incredibly high resolution here, and you ended up with just single lines, the intensities would just directly be equal to the heights. But with width, that's going to look like that. That making sense? Okay. And so these would be your three possible values for B local. Remember, B local is your magnetic field local. And you can think of this as your different spins, or one other way of thinking about this is you have little magnets that are next to each other, right? And this would be the magnets pointing in different directions. Okay. So if you were to take three magnets and flip them upside down, this is what you would see. You'd have these different combinations of repel and connect, right? And that's it. That's all that ever was. Okay. Okay, so this is actually the four possible values that gives you your quartet. So here we have a quartet. Again, it's because we have three chemically distinct hydrogens over here that are affecting this. Okay. And they're chemically distinct because of the things off of here. Right? This stuff over here that we're not seeing. Because it's just not important for what we're doing. All we need to know is the colors, that these are chemically distinct, right? Okay, so if all three of these are perfectly matching up, we're going to get this one over here that shifts the least. If all three are matching the opposite way, we're going to get the one that shifts the least. And that's going to be the smallest one, right? If we get one that doesn't match, we're going to end up with this next one, aren't we? And then two of them being down is going to give us this one over here. And that's just the probability distribution, isn't it? Same sort of thing you would have done in a stats class. Okay. So let's talk about Pascal's triangle. So this right here would be Pascal's triangle. You can see that this actually gives us that distribution if we were to just add these numbers together going down in a triangle. Makes life a little easy, doesn't it? So a singlet, for example, is a 1, right? Doesn't have anything next to it to add, so you'd go 1 plus 0, that gives us 1. 1 plus 0, that gives us 1, because there'd be zeros over here, right? Okay. And then we go down, so we go 1 plus 1 equals 2 down in the middle. And then 1 plus 0, 1, 1 plus 0, 1. And you can just keep going down to whatever you want to do in terms of multiplicity. Okay? And it'll give you the distribution of those. Can everybody say that okay? Again, you just add the numbers above to get the one between. Every single time, it's going to extend one more state. Can everybody say okay? Okay. Fantastic. Again, this goes up to quintet right here. We can go beyond quintet. We can do multiplets of whatever we want. It'd be pretty unusual to go beyond quintet, but if you ever do something really advanced, maybe you will. And you'll do something pretty crazy. You can make like a C60 cage. Or you could make a very complex cage compound. Okay? And you'd get multiplets where you'd have more than 4 things off it, right? Okay, so let's go ahead and look at some different ones that do not usually exhibit coupling. And so these NH2 protons, they are not going to be coupled to any of the other protons that are on the carbons. Okay. So that seems like it's violated, doesn't it? These are coupled, right? Can you see the coupling from those? Yeah. So we're still getting the coupling, aren't we? Okay. And we can see here, this is 4 of them, right? And that comes from this having 3 hydrogens there, doesn't it? Okay. And then this one's 3 of them right here, and that's these ones right here from having 2 hydrogens. So 1 plus 2, isn't it? Okay. This one doesn't have the extra, so does it? That's just getting spin-spin coupling from CH3. We're not getting it from H2, are we? That would give us more coupling, see? Okay. And so these give us a very broad singlet right here. We don't see any splitting. So you don't see any splitting. You don't see any coupling, do you? Okay. Okay. All right. So how about what do you think would happen with an oxygen, maybe? Yeah, it's very broad. But what else are you sort of seeing here? What do you think would happen with an oxygen, like an OH? It'd be a similar pattern, right? And again, you're not getting that coupling, are you? Okay. So, does anybody remember anything about carbon hydrogens versus oxygen or nitrogen hydrogens? Mm-hmm. Exactly, and they're more acidic as well, aren't they? Okay. And so what you're going to see a lot is that these right here tend to exchange so fast that you can't actually see them in the NMR here. So instead of getting a splitting, you just get a very broad peak because you're just seeing a bunch of different small states difference. Yeah. So it's just a mess instead of coupling. Okay. All right, so these are some commonly encountered coupling constants right here. These would be in our hertz here. So they're very, very small values. Okay. So notice that when we looked at the coupling, these are very, very small differences, right? Okay. Rather than these much larger differences that we were measuring in ppm. Remember, ppm were divided by like 300 megahertz, right? So these are values that are usually in the megahertz sort of ranges. Okay? That's why these are so tightly grouped together, because the difference in coupling, it's only very tiny differences in the hertz range, rather than megahertz being millions of hertz, right? Okay. And so right here, we see the hydrogen next to a hydrogen on a carbon like that. That's going to have a 6 to 9 hertz coupling, and that's why we actually see those. Okay? They're real close. We need pretty high resolution, but we still see them, right? This right here, if we look at it, the next one over, so instead of the alpha, we have the beta position. Those are approximately, they'd be fractions of hertz, okay? And so we don't see those because they're just too closely grouped together. Now, if you had a high enough resolution instrument, you could see that very, very little, okay? And you can actually do that. You can do various different types of scans where you can actually start seeing the coupling from the one over another spot. Okay. But that's much more advanced than we're going to go into in organic chemistry. So this would be your double bond here. Notice that the double bond actually causes these to couple even more usually. And so you're going to get a slightly higher one. Okay. If they're on the opposite side, this is actually going to cause that coupling constant to be a little higher. And so you'll get an even larger split. This is where they're geminal. And you can see this is actually very small. You can still see it on a decent instrument, but if you don't have a particularly new instrument, or if you don't have a good quality instrument from back in the day, you may still not even see these geminal ones. This right here is off the carbonyl, and again, that's very small range. This is off of the other side of an aromatic, and notice that if you have a good enough instrument, you can actually see the coupling from across the aromatic. Okay? And so the aromatics can actually be some interesting, very interesting patterns. So keep in mind, if you have coupling within coupling, splitting within splitting, you could actually cause splitting of your splitting peaks. Okay. Okay, so let's go ahead and see some examples of these. So here we have some coupled protons right here. These are the ABs. So that's these two right here. See those? And so we have one next to it, and that caused us to have a doublet, doesn't it? And then if we measured the difference between these, we'd see that they're about 8.5 hertz. And so that would give further evidence that we're somewhere on an aromatic, right? Or maybe like a double bond, right? Okay. It's something a bit higher that's more like a double bond aromatic, right? Rather than necessarily opposite sides of a double bond. We know that they'd have to be the same sort of side as a double bond, which is, again, aromatic. Okay, and we go along and we see C here. And so we see that C is going to be coupling with D here. Why doesn't it couple with B, by the way? Not Jason, exactly. This is a very common problem people run into, is that they kind of skip mentally. They sort of bridgehead carbons that are at the joining points. And so please be careful that you sort of reglance, relook. Okay. Okay, and so we see that these actually come out as 7.6 hertz, and you see that those are more consistent with the numbers you would get from a carbon-carbon, right? Notice that there's a fair amount of overlap. I would not use this as your primary identifier, right? What would be the primary identifier of which hydrogen is where? So how about these right here, the ppms, the chemical shifts? Yeah, that'd be your big identifier, right? So you look here, we have, this is 7.4-ish. See that? This one here is about 7 point, a little above 7. And so these are very, very high chemical shifts. And so that gives a lot of support for it being an aromatic hydrogen, right? And then over here, we only have something at 2.6. And so that would be the next one over from something like a double bond or aromatic feature, right? And then we go here, and it's just a little bit over 1 at a 1.2 something. And that's the sort of thing you'd see for a CH3, right? That next one over on CH3, okay? And then you'd start building your case, right? Okay, so if I have a structure like that, what should I look at? So I would have two different hydrogens here because I have groups on both sides here, don't I? They're chemically distinct. And so I'd have a coupling there, wouldn't I? And so I would go, okay, A has a split. That indicates it has one other hydrogen that's coupled to, right? This one here also has a split. That indicates it has one other hydrogen it's coupling with, right? Okay. This one right here, that's a quartet, isn't it? And so how many hydrogens do I have to be interacting with, coupling with? 1 plus 3, right? Yeah. And that gives me evidence for that being a CH3, doesn't it? And then I come on over here and I have my hydrogens here, and that's only a triplet, isn't it? So 2 plus 1, that means I have to have two hydrogens on next to it, don't I? Okay. And so you build up a case with the evidence that's being presented to you, right? All right. Let's go ahead and look at a more complex signal splitting. So the splitting that we tend to observe when the protons that produce a particular signal are going to be coupled to two or more distinct types of protons. If these separate types of coupling have sufficiently different coupling constants, then we're going to actually observe a complex splitting, which is what we're seeing right here. Where notice it doesn't have that nice, high, low. See that? It's low, high, low, high. That's not the splitting you would have expected, right? It should have been like a Gaussian distribution sort of looking thing, right? That's not Gaussian looking, is it? And so what you're seeing here is this is actually complex splitting, where you have sufficiently different splitting constants that they're not both interacting on the same thing, okay? This is a different set of splitting interacting with a different set of splitting over on the other side, all right? So in this case, what we have is we have geminal, and then this being trans, this one being cis, right? And you notice if you go back to your chart here, the geminal had almost no splitting. See that? Very small splitting constant. And then the trans had a very large one, and then the cis had much larger than Gemini, right? And so what's going on is you actually are having your split and then another split of those. Okay? And you actually get two sets of splitting. Okay? All right. So again, this is 3 chemically distinct protons, giving us 3 peaks, right? Say okay. This is your A right here. That's your B. That's right there. This is your C right here. So if we zoom in on this, you can see them, all of them, but this one's probably the easiest to look at. Okay. Though this one actually identifies it the best, if you will. And that's that what you're actually getting is you got split, and then those are splitting individually, aren't they? Can everybody see that? So you're getting your large split, and then you're getting your small split of those 2 peaks. Okay. Can everybody see that pretty clearly from this one? It's a little harder to identify that here because you're actually getting pretty even splits, aren't you? Yeah. Okay. So again, you have, for example, HB. This is coupled to HC, so HB here, coupled to HC. The coupling constant there is a 7.1, right? Okay. And HA would be coupled to the HC, and that would be a 14.9. And so that's actually what we're seeing here. That's at 14.9. Right? And then your other one you'd couple with would be a geminal, and so that would only be a couple, right? Very small. And that's what you're seeing right there. Okay, so let's look at that splitting diagram if we were to go ahead and write that out. So here we see the HB right here. And so we do the large one first because that's going to give the majority of our splitting, right? Then we need to center around those 2 large split peaks. Okay, so we split those by 7.1 and they'd be even. They'd have the same heights. Okay? And so that would give us our 7.1 right here. And that's being split by this HC over here. And then we'd get the split from the geminal right here. And that would only be a 1.8 hertz split. And so you see that we doubled our singlet on this side, right? So we double the doublet. Okay. Is everybody okay with that? So what is that called? Doublet of a doublet, right? Okay. This. That's a doublet. Because you double it, a doublet, right? All right. Now, this one right here is going to, again, be the HA right here. So HB, we split with HA. And then we're going to split with HC here. And that would give this doublet. Okay. So we get the same splitting pattern, but what we would end up getting is we would get a different distribution of the peaks. So if you look back here, this is more like case A, isn't it? Large split, then small split, right? Okay. This is more like the other case, isn't it? Small splits, so they end up mixed together. Okay. So this was going to be a triplet of a doublet. So we have a triplet first, right? And then we have a doublet layered on that. And everybody said okay? And so we end up with 6 peaks, but that's not because we have 1 plus 5, right? We'd have 1 plus 2, and then a 1 plus 1. Okay. Okay, and so that's this case right here. So let's look again at the signal resolution and the strength of our B external field. So these right here give us overlapping CH3 signals, and we can see this is quite a little mess of stuff. You can even see little places where they basically are overlapping, and our resolution can't separate them. Can you guys see that, where it's uneven? It's not like a symmetric peak. like right there. Okay. And so this is actually this compound here. This is taken with a 90 megahertz spectrometer. And a 300 megahertz spectrometer is going to be our next slide, actually. And so what you're noticing is this 90 megahertz spectrometer has a much weaker field, doesn't it? Okay. And so that weaker field causes less splitting up between the peaks. It can't resolve the difference between the peaks as well. Okay. And so everybody's taken a picture where you're not zoomed in properly, like through a fence or something. And the individual fences are all blurry and you can't separate the different fence pieces, right? Okay. That's what we're seeing here, isn't it? It's blurry, and so we can't completely separate, so we get a composite of the peaks. All right? Okay. And what would this be called? They're not resolved, right? So these peaks right here, for example, are not resolved. These two right here are also not resolved. Okay? We can't actually see the peaks for them well enough to identify the peak position. Mm-hmm. Yes. Not resolved. Okay. So this one's taken at 300 megahertz. So this is a 300 megahertz instrument. It has a more powerful magnet. And so what you can see is now we can actually resolve that splitting, can't we? Say we got clear, nice individual peaks. Right? Now, this is important because, yeah, and we can usually get 300 megahertz instruments in hydrogen, and great, congratulations, that's wonderful. But if you start looking at things like carbon, oxygens, irons, which would be the sort of stuff you look at for MRIs, okay? The magnet very well may not be strong enough to resolve everything, okay? And so what you'll see is you'll see a lot of this sort of thing, okay? Hydrogens, it's pretty rare nowadays to see this sort of thing, unless you're using like a desktop instrument that's very, very, well, I don't want to say cheap. I want to say like very small so it can't have a big magnet. It's running off a socket on your lab bench, right? And so you can't run enough electricity through it to get a very strong magnet. Okay. That's usually where you'd see that sort of stuff nowadays. Okay, so remember that the coupling constants are actually going to be independent of the B external. So regardless of the B external, your frequency differences between the split signals going to remain unchanged. You just may not be able to actually see them because all your peaks are too dang close together. Okay? So you may have them not resolved, but if you were to take and measure these differences up here, you'd come up with the same differences for those splittings. Okay. All right, so this right here is the dependence of your resolution on your magnetic strength. So again, these are your unresolved peaks. Signals right here. They were the peaks that have not been resolved before. Oh, ouch. And these ones would be your resolved peaks right here. And you can see that they have split right there. Everybody see okay? Okay. And why are they splitting here? Notice these separations right here, they haven't really changed, have they? They're the same in both cases, right? Okay, that's because your splitting doesn't change based on the magnetic field external. Okay? Those are magnetic field local phenomena. But what does change is your splitting of your overall peak distance from these. Okay? And so what we see is we resolve them between here. These frequencies actually will move apart, and that's because you're getting a larger amount of space for your chemical shift. Okay, and so again, this would be your frequencies. These would be your chemical shifts. So you notice here, we would have this, and we may not be able to actually resolve any of it, and so we'd have this very wide peak, right? And we'd identify it at somewhere here, right? when we increase the strength of our magnetic field, this is going to convert to a chemical shift increase that we can narrow that peak for our chemical shift. And what we'll see here is we can actually now resolve exactly where this is in terms of the chemical shift. Okay. Okay. Are these going to be completely different numbers based on the magnetic field? No, because when we figured these out, right, we were always dividing by the magnetic field, weren't we? So these numbers, these chemical shifts, the reason we use those chemical shifts is that they are chemical field dependent, right? So another way of saying that is we have normalized them using TMS. Okay. Okay. And so the numbers will be essentially the same, but we'll be able to resolve where it is with more detail. Okay, so this is carbon signals right here. This is where you're going to see a lot more noise and a lot more unresolved features. And so this is going to be where we're going to take a carbon-13 NMR. And again, remember that we need an odd number, so that's why we're going to use carbon-13. Okay, because that's going to have an uneven nucleus, right? Now, having said that, how much of a sample is carbon-13s? Yeah, about 1%, right? And so that means that the amount of signal coming off our sample is actually really small, right? If we were to look at the other stuff around our sample, those are going to be much larger, aren't they? Okay. And that's why you get a lot of noise in this. Can everybody see the background right here, the noise? This is noise. Okay. It's random fluctuations due to things like the radio signals around you, due to electricity changing, etc. Okay. And so compared to those in carbon-13 spectra, you get a lot of noise, okay, compared to the HNMRs that we looked at before. And so we're going to go ahead and do TMS again. And we're looking at the shifts off of TMS. And again, these are going to be for the carbons, right? So you'd look at the carbon signals here. Okay. All right. So when we look at the carbon-13 versus the HNMR, what we're going to notice here is that it is very, very, very similar. Okay? We're essentially going to have the same analogous things happen for your carbon-13s. It's just going to happen in a different place because it's a heavier nucleus, right? And so you're going to have a gyromagnetic ratio that's going to be about 1/4 of that as the proton. And so what you're going to see here is that if you were to take this spectra and take an HNMR and have them as the same chemical shifts, what do you notice about this chemical shift right here? What was a really large chemical shift in hydrogen? What's a really large chemical shift in hydrogen? Like a 10, right? And so in carbons, that's not a large chemical shift at all. That would be all the way over here, right? Okay. And so what you'll see is that carbons, because it has a much, much smaller gyromagnetic ratio, you need a much stronger magnet to split them apart. And you end up using a much stronger magnet, and everything gets shifted far, far, far to the higher chemical shifts. Okay. And so, let me see, is there anything else I need to mention here? Remember that we're going to get for HNMR, we would have the chemically distinct protons, right? So if we look at C13, what would we see? Chemically distinct carbons, right? And so, for example, in this one right here, what would you expect for chemically distinct carbons? 3, right? 1, 2, 3. Because we have them coming away from the chloride, don't we? Okay. And that's these ones right here. You notice there is another peak that you can actually see right here. somewhat difficult to resolve until we go ahead and filter out some of the noise. This is called signal averaging, by the way, where we take multiple peaks over and over and we average them together to boost our signal. The noise, because it's random, tends to cancel out. You can see it both as negative and positive above this line, right? Okay. And so we've done that. And we see one more peak, and that's actually the CdCl3 solvent. Okay. That's because we needed solvent to keep this suspended. All right. Anybody have any questions about that so far? No? Right. So what do you know about the hydrogen versus carbons? What's the difference between those? You didn't see any splitting in this case right here. But, so you would still have the same up-down splits. That's still totally doable. C13s definitely have same spin states, and would split. But how common are C13s again? 1%. So the likelihood of having two C13s next to each other? Yeah. And so you're exactly right. We didn't see any splitting because the chance of having two C13s next to each other to cause the splitting is 1 in 100 times 1 in 100, right? 1 in 10,000 chance. So technically, you probably are seeing some splitting, but it's so small that it's down here in the noise. You just can't resolve it. Okay? Very, very difficult to see the splitting. However, under the conditions that spectra are required, we don't usually observe a coarse signal splitting. Again, we would still have that same splitting if we had two C13s. Why doesn't it split off of the C12, by the way? If something's symmetric all the way around, does it matter if you're spinning it this way or this way? No, it's the same damn thing. It doesn't make any difference spinning it, right? If we don't observe splitting of a carbon signal by attached protons, that's actually because the broadband decoupling is essentially turned off for the coupling between the C13s and the H1s. So again, the H1s have their own magnetic fields, right? So your C13s that are within these hydrogens, they have those H1s working on them, don't they? Can everybody understand that part? So the H's are spin-spin coupling with those carbons. Okay? But what we do is, because carbons have a lot of hydrogens on them, right? So if we were to look at a spectra with the hydrogens causing splitting, it's going to cause a lot of mess. Okay? And so oftentimes what happens is we essentially do an operation that's going to remove that spin-spin coupling for the hydrogen portion. Okay? And then we add that back in as data points later so that we can actually identify what the hell our carbon peaks are, right? And how many we have. Okay? All right. And this is actually what's referred to as broadband decoupling. And broadband decoupling is literally what it kind of says. It's decoupling of the hydrogen and carbon spin-spin states. Okay? All right. Let's see. Oops. All right, so this right here is your chemical shifts for different groups again. Of course, in the case of our TMS, we're going to have the 4 carbons on that, and so we can still use that as our 0, right? And so we'll still use that as our 0. It's just in this case, we're detecting the carbon portion of it, aren't we? Okay. And then we would look down here and we see that the CH3 is going to give you a peak somewhere in the 10 to 25. Notice this is going to be the exact same pattern as the hydrogens, right? It's just going to have a larger chemical shift because it has a quarter of the gyroscopic spin. Okay, this one right here is the CH2s. That would be with 2 carbons attached to it, and that's going to give us somewhere in the 20 to 45. 3 carbons attached, 25 to 45. This one has 4 carbons attached, and that's going to give us 30 to 35. Remember, again, we'll have more shielding going on. and so we have more shifting. More hydrogens you have, more hydrogen, more electrons you can take from them, right? More shielding you can have. Is that making sense for everybody? Okay. Less hydrogens you have, less electrons you can take from them, less shielding, right? Okay. This is with a chlorine attached to it. What is that chlorine going to do? It's going to pull electron density away, right? And it's going to de-shield that carbon, causing it to have a larger chemical shift. Okay, so this is our double bond again. Remember the double bond where it caused a reinforcement of the external magnetic field? Guess what it's going to do here as well? Reinforcement of that external magnetic field, right? Same sort of patterns, same relationships. This is an aromatic carbon. Does anybody have any questions about those so far? Okay. Notice again, it's the exact same pattern, and you can get a pretty decent approximation if you just take the hydrogen numbers and multiply them by 4. Okay? They won't give you perfect numbers, but pretty decent. Okay, so let's go ahead and look at some of these integrations of these C13 NMR signals. So we go ahead and look at the C13 NMR, and what we see here is we have some chemically distinct carbons, right? Which one is going to be the one that goes way far out? Very high shift. Yeah, your double bond oxygen, exactly. Which one is going to have a fairly low shift? Your CH3s, right? And you see you have 2 of them, don't you? They're pretty close together. Pretty simple. Okay? Okay. Now, we do have one difference that we need to identify here. Notice that, for example, we have 1 carbon here. There's 1 carbon here and carbon here. These should have 1 carbon as well, shouldn't they? We shouldn't have multiples, do we? But what do you notice about the areas under these peaks? They're pretty different, aren't they? Yeah. And so what you end up seeing is in C13 NMR spectra, the area under the peak is not going to be proportional to the number of carbons, atoms, that are contributing to that peak, okay? It doesn't have almost anything to do with the number of carbons, right? And so the number of carbons, not helpful, okay? The area under the peak is still useful, though. Just remember that is not the number of carbons, okay? The poor correlation between those C13 number of carbons and the area under that peak is actually a factor from that broadband decoupling. Because we've done the broadband decoupling, that actually is what's causing that, okay? Because we're overriding it with another source of intensity, right? Now, this broadband decoupling tends to magnify each carbon signal through what's called a nuclear Overhaus effect. Haus is in like the German word. So Hauser. Okay. So nuclear Overhauser effect. That's going to be a magnification that occurs to different carbon atoms. So our integration has no value in terms of the height of the peak. If we take a direct integration and try to get solid numbers off of that, it's not going to be particularly valuable. But you will notice an overall pattern, and that's the number of hydrogens does tend to play a little bit of effect on there, okay? Loosely. But again, I would not use the integrals for these as a major source of data, right? These are going to be the positions that are going to be the most important. All right, so let's go ahead and take a little bit of a deeper look. So this is DEPT 13, C13 NMR, and we can go ahead and talk a bit about 2D NMR. There's also a thing called 3D NMR. We probably won't touch on that because we have certain limits of time. But 2D NMR is extremely useful for determining where these groups are in relationship to each other. Okay, so DEPT, this is distortionless enhancement by polarization transfer. So this is going to give you a spectra that the signals are given off from the C13 nuclei, depending on the number of protons that are attached to these carbons. DEPT spectroscopy is usually summarized in a normal broadband decoupled C13 spectra so that you can read it alongside as like a little bar. Okay. More often than not, you'll actually see these grouped together. So you would see an HNMR, a C13, and a DEPT. And the HNMR would be the large one. C13 will be slightly smaller because you don't need the integral as much. And then the DEPT would be a small little bar at the top, okay, right above the C13, right? So that you can look and see how many hydrogens relative there are. Okay? All right. So this right here is a cozy spectrum. This is going to be a variety of two-dimensional, 2D NMR spectra. The ones we've done so far have been one-dimensional because they only have a frequency axis in one direction. So in a two-dimensional, we're going to have a frequency axis in 2 dimensions. Okay? And you'll see that we'll get groupings of these bands. When we're looking down, the intensity of the marks is going to have to do with the intensity or integral, right? How much they're grouped together. Okay, so we're actually technically seeing a third dimension, which would be the z-axis, which we're looking straight down on, right? That's what you're looking through. Okay, so in a cozy spectrum, you're going to have the 1D proton NMR spectrum that's shown on the x and y axes. Your peaks are then going to appear on a diagonal axis where they overlap. And so here we see some peaks. For example, this right here would be the hydrogen B right there. This one here is the hydrogen C. Okay. So by doing this, we actually get one more piece of information, and that is the cross peak here. So B and C give us a cross peak here, and that actually shows us that they are extremely close together. Okay. And so what this does, this 2D NMR, is it shows us the ones that are being coupled together, the ones that are extremely close together. And so, for example, we can see here that the one that's right off the ether here, on the other side of the ether, once we identify B, then it's the one that has the CH3 next to it, because it's coupling with it. Okay. Whereas if we were to look at the A, which is here, we notice it does not couple with those, does it? See that? And so we can then go, okay, this A1's off on its own. It's not near these other two features. Can everybody see that okay? Pretty cool, huh? Mm-hmm. Because they have a cross peak. So, no, there's nothing there. See that? So this is A right here. All your peaks are on diagonal. So this is the B hydrogens, this is the A hydrogens, this is the C hydrogens. This then is the coupling down here, which is the cross peak. Yeah. So like these are our actual hydrogens for those different groups. That would be our HNMR spectra, normal HNMR spectra. Okay? Is in this diagonal right here. Because what's going to happen is your 2HNMR is going to give you the exact same position for those groups. Okay? The ones that are off of this diagonal are cross peaks. Those are going to be because of coupling. Those are going to be because those two groups would be close together. So for example, if we were to identify these different groups here, B here is a chemical shift of 4. And that's because it's just off an ether, right? And then we go here, that's a chemical shift of 2. And that's because it's the next one over from a carbon. And then this CH3 right here is a little bit above 1, right? 1.2, 1.3, something like that. That's because that's the CH3, right? And that's these peaks right here. And then you would come off of that, and these would be the cross peaks then. And they show coupling. They show that these are near each other. Okay? That they're near enough that they can couple together. And so this doesn't have any coupling. See, there's no peak right there. There's no peak here either, is there? And that tells you that A doesn't couple with either of those. So it's not nearby either feature. C and B, though, have a cross peak. And so that tells you they couple and they're near each other. Okay? Because they have to be near each other to have significant coupling. Right. And so if you do this with a very high resolution instrument, you can do this over and over and over and assemble down the chain for whatever you want, including a protein. Okay. Anybody have any questions on that? Okay, and that's COSY. For anybody that's in biochemistry or whenever you go into biochemistry, you may actually recognize this name if they talk about decoding proteins and protein structures. Because COSY, and then they usually use another technique alongside it, is actually how you do a lot of those. Okay, so this is HETCOR, HETCOR, and it stands for heteronuclear correlation spectroscopy. So this is another very common 2D NMR that you'd see. In this case here, we have our diethyl phthalate. So what we would see here is we're actually going to have two different spectra that we're going to put on each axis instead of doing HNMRs on both. And this is going to be your C13 on the bottom and H on the side. Everybody said okay? Hydrogen here, carbon down here. Okay, very good. So what this is going to give us is each cross peak here is going to provide information about which protons are attached to which carbons. So if we look here at these red arrows, we can see the two peaks here. Now, it won't be a diagonal line, right? These will not have diagonal lines here because they're totally different spectra, okay? They're just not going to match up in the same positions. Okay. So you see your normal carbon peaks over here, your normal hydrogen peaks coming along here, right? Okay. But what we'll be able to see is that the ones that have the cross talk are the hydrogens that are the ones attached to those carbons. So these hydrogens are the hydrogens attached to this carbon right here. And that's because it has this right here, this cross peak. Okay. Everybody okay with that? See that little peaks? So for example, where is the hydrogens that are attached to F? Right there. And see this cross peak here? That tells us those are the hydrogens right there. They're attached to the carbon F. Everybody said all right? Okay. It's just a really, really useful way to look at these because our brains actually do a good job correlating these things. If we were to look at those peaks separately, our brains don't do a very good job of it. And it becomes much harder to figure out. Now, notice that these give us distinct information. So when we do very complex compounds, we can actually take these pieces of information and large compounds, we can resolve which hydrogens are attached to which carbons in which order. And so we can get pretty good structures, though please keep in mind that oftentimes this has no ability to resolve enantiomers. Okay? It's something that people get tripped out a lot, is it doesn't actually give you the three-dimensional structure. It gives you connectivity. Okay. You can get some three-dimensional structure information, but not everything. And so don't think this is the end of everything that you could ever do. Okay. Very common mistake companies make. So let's talk about some of the structure strategies for success here. This is my little like table of things to go through. What I would actually recommend is as you do problems, you kind of have this table up. And when you're first starting problems, you use the table. Eventually, the important parts of that is going to ingrain itself, and you're going to be able to just go through and do them, right? Okay. I.e., this is a nice way to structure yourself to practice. Okay. Okay. So some of the informations that are obtained by H&MR, this is going to be your number signals, right? And that's going to give you your chemically distinct types of protons. Your chemical shifts, so different chemical shifts tell you different sort of functional groups, doesn't it? So for example, the aromatic rings, very high, double bonds, electronegative atoms that are near the protons are going to give you those moderate shifts. And then very low shift tells you doesn't have anything pulling electrons from it or reinforcing the magnetic field nearby. Okay. The integrations for the H&MR actually tells you the number of protons, but keep in mind again, it's integration. It's the area under the curve. Okay. Not the heights. Please don't get fooled by that. Right. The splitting pattern, if you have the splitting pattern, you will not have splitting patterns on every single spectra. Some of them will be purposefully given as low resolution spectra, just so you can see the peaks where they are. Okay? And you can get their positions easier. But if you have splitting patterns, then that's going to tell you the number of neighboring protons that are distinct from the protons that are responsible for our chemical signal. Okay? So the ones that are different than the one you're looking at. They're nearby. So what do we get from C13 NMR? So we get numbers of signals again that are from the chemically distinct carbons, and that tells you how many different chemically distinct carbons there are. Keep in mind, though, that solvents are often more of an issue in this case. It's hard to deuterate all the solvent, and then your amount of C13 can be fairly small, right? So your chemical shifts, so a normal chemical shift, it's going to tell you if you have an aromatic ring, do you have a double bond, is there electronegative atoms attached to it? If you have larger shifts, it could be multiple electronegative atoms. You have very large shifts, typically a double bond or aromatic, right? Okay. And so let's go ahead and take some of the steps for determining interpreting our H-NMR spectra. So number one is always to determine your number of proton signals, because that tells you how many distinct hydrogens you have to deal with, right? So number one step always, how many distinct hydrogens do I have? How many distinct peaks do I have? Okay. Then the next thing I'm going to do is I'm going to take those signals. I'm going to analyze those signals. So I'm going to take the chemical shift first. I'm going to analyze that. What possible groups could that be? Could that be aromatic? Could that be a double bond? Could that be a chloride? Okay. Then I'm going to consider the relative integration. So I'm going to consider how high the peak is in terms of integration, right? The intensity of it. Okay. And that's going to give me how many. But again, keep in mind that's the area. So you kind of have to play it a little bit loose unless you have the integral. Remember the integral? Where it goes along, goes up. Okay. In which case you can just directly measure. The height of the integral will measure. You interpret then the splitting pattern. This is your last step that you'll want to use to sort of like identify, hey, which groups are attached to each other? Okay. What order do these come in? Right. You can also use it to verify things that you've already come up with. I think this CH2 is the next one off the carbonyl. Then the CH3 has no shift, so it has to be the next one. And that would give you a splitting pattern, and you check the splitting pattern against the splitting. Okay. So number 3 is going to be building your molecular fragments. Typically when you do NMRs, you are not going to just get a structure period. What you're going to get is parts of the structure. And so I have a carbonyl. It has a CH2 and a CH3 probably. Okay. And then what's the other side? Well, we had another CH3. So that makes sense to be on that other side then, because it didn't have any splitting from my other CHs. Okay. And you're going to assemble these pieces into a full structure. You've actually seen me do it a couple times. If you remember, like where we did the ether, that ester I was talking about, well, this one has to be this side of this. And then the splitting tells us that's associating with the CH2 here. And then we have another CH3 real close here that is more shifted. So that has to be next to the carbonyl, doesn't it? Okay. And that's what I was doing, actually. I was actually building my molecular fragments together, wasn't I? Okay, so we're again going to next assemble the identified molecular fragments. The best way to think about these is you have a puzzle that you're building the pieces for, and then you're going to assemble the pieces, right? Kind of like you do with actual puzzles. Anybody assembled a puzzle? You look at the box, you go, okay, this has weeds on it, they're green and blue. Oh, this has straight little green and blue things. Okay, then that's part of that, right? Then once you have those gathered together, you assemble them into a more cohesive picture, right? And that's true for almost every science thing, right? You always want to take it, break it down, and then assemble it together. Okay? So this is an unknown right here. So let's try to go and apply these steps to interpret this spectra right here. We have here, we did GCMS. We got a C10, H12, O2. Okay? And so we know kind of what sort of groups there are on this to a degree. But we have no idea, are those carbonyls? Are they alcohols? What are they? Okay? Ethers, anything. And so what we want to do now is we want to take this H and R, right? And we want to identify these peaks. Okay? Can you guys look back in the tables? So what's the first step again? Yeah, how many different chemically distinct protons do we have? Okay, how do we figure that out? So we'd look over here. This is 0, so that is TMS, right? Okay. And then we have one right here. So that's one chemically distinct hydrogen, right? Then we have another one here, and that's another one, isn't it? Then we have one here, and that's the third one. And then we have one here, and that's the fourth one. And then we have one right here, don't we? So we have 5 chemically distinct protons, don't we? Their positions would be, well, this one over here, if we look closely, is something like 1.1, right? ppm. Our next one, if we go up, is something around 1.8. Our next one, if we go further, is something around 4.2, isn't it? We go up the next one, and that's going to be somewhere around 7.4. And then we have an 8.1 here, don't we? And so those are our 4 chemically distinct hydrogens. We take those ppms, those shifts, right? And then we can look at our table. Okay. So we go and look back at our table. And I actually have a copy right there with these values. So if you were to look back at your table, these are the ones that would make some sort of sense. Okay. Now again, don't forget, some of the same rules that existed before still exist. So for example, the number of carbons and hydrogens still gives us information, doesn't it? Okay. So if we look at this, do we have a saturated hydrocarbon here? No, we're quite far away from it, aren't we? And so we can figure out our IHD and use that to help us figure out what makes sense. Do we have a single double bond here? No, we have to have a lot of double bonds, right? Okay. Okay, and does everybody remember how to get our IHD? Exactly. So we 2 times the 10, right? 20 plus 2, 22. We'd have 10 less than that divided by 2, so we have 5 IHD, really. Okay, and so the groups that make sense on here, well, we have a 1.1-ish group, And that makes sense to be a CH3 of some sort, doesn't it? Okay. And then we have a 1.8, and that sounds a lot like something like a CH2. Okay. And then we have a 4.2. Now we have some sort of oxygen group, and so this makes a lot of sense to be a carbon off of an oxygen. Okay. That would give us something consistent with a 4.2. And then finally, we have that very high one, right? And that's usually something like a double bond or aromatic. In this case, we have a lot of IHD, so it makes a lot of sense to be an aromatic. Okay? So that's very consistent with an aromatic group right there. If we look at our relative integrations for these, what we would see is that we have a 1.5 here. Does everybody remember how to read this? So all you got to do is you just measure the distance here. Okay? So from here to here, that's going to give you that relative integration. From here to here, that's going to give you your next relative integration. And we can keep doing that. And again, that's going to give you your relative integrations each time, which is the area under those. Mm-hmm. Typically, it tells you. So this is the one right here. So the difference from here to here is 1. And it's usually done in a relative scale. So usually what happens is it takes the smallest value and it divides everything by. And so what that then does is it gives you 1 hydrogen, 1.5 in this case because it's 0.5 larger than this one. That making sense? Yeah. If you have to, what you can do is you can just take a piece of paper, find the smallest one, put the split on your smallest one, and then measure it based off of that. Okay? So for example, I would take a piece of paper, I'd trace these out onto that piece of paper, I'd bring that paper up here, and I'd go 1.5 of those. And so you can actually make your own ruler just by going to the smallest integral. Mm-hmm. Take a piece of paper, just make 5 markings usually, based on the smallest integral. So literally take a piece of paper, mark, mark, slide it down 1, mark, slide it down 1, mark, and do that to make a rule. Okay? If you absolutely have to. Normally these are labeled though. The programs almost always label them. You have to actually go back and remove the labels. So, however, sometimes people do that. So the next thing we would look at is this would give us our relative numbers of hydrogens here. And so in this case, we would actually go ahead and add these together, and then we divide by the number of hydrogens we actually have, and that would tell us that we'd have a multiple of 2 for everything, don't we?
There was 5 distinct hydrogens there.
Mm-hmm. Yeah. So 5 distinct, 1, 2, 3, 4, 5, yes. And if you add all these together, then divide that 12 here, what you'd end up finding out is this actually has 2 hydrogens. Okay. And so the next thing you would do is you go to your splitting patterns, and you'd see how many hydrogens they have next to them, don't they? Okay, so for example, this right here has 5 distinct hydrogen patterns because it is a sextet. So there's 5 distinct hydrogens around it, which would have to be your CH3 and CH2. These ones right here is very complex, and so you would just ignore that because you can't really resolve it. Okay? They don't even blow it up for you. Over here, we have a triplet. So that tells you that hydrogen here has to have 2 hydrogens next to it, doesn't it? Okay. And so here we have our molecular fragments, and we would assemble these molecular fragments together. Okay. Do I have shit, I'm out of time. Damn. Okay, so try the homeworks. let me know how the homework goes, okay? Yeah. Everybody started on homework? No? Okay. Attempt the homework. So let me know how it goes. Okay. The next part would be putting these peaks together, right? Okay. How much longer do we have till the end of the semester? A little bit over a month, right?
Yeah. 5 weeks kind of.
Okay. So I can give you guys Monday exam, but I'll have to spend most of the day on Wednesday covering the next chapter. Okay. Is that the vote that everybody would prefer? Okay. Okay, we're gonna have a pretty quick turnaround to the next exam, okay?